Okay, well, we're back with our sixth video here on polynomial functions, and we're going to take a polynomial given to us in the general form and we're going to find the factored form, which is really equivalent to finding all the roots and their multiplicities. So that's what we're going to do. We're going to try to basically use our graphing calculators to help us find some roots, or at least approximate ones. Any of these that turn out to be a rational number, we can use synthetic division then to divide out and see what the factor is that, well, we know what the factor is that corresponds to it. When we get a zero remainder, we'll know that that factor is the x minus that root is a factor, and we'll know what the other factor is, which will be a polynomial of one smaller degree. That we call that the depressed polynomial, and it has the other roots. So we continue in this manner to divide out until finally we get the depressed polynomial down to a quadratic. If it's a quadratic, we can polish off the last two roots by the quadratic formula. So in this manner we can find all of the roots of any polynomial that has all rational roots or all rational roots except for two. It turns out that there is a quadratic formula. We know how to solve any linear equation. We can solve any quadratic equation. It turns out there is a cubic formula. It's a little harder to write down than the quadratic formula, but there does exist such a thing. And as you might suspect, it has cube roots in it. You have fourth roots or square roots of square roots inside of a quartic formula. But when it gets to a fifth degree polynomial function or higher, there is not and can never be a formula for solving them. So if I just arbitrarily write down a fifth or sixth or seventh degree polynomial function, there's absolutely no way to solve it. And even for a third or fourth degree polynomial function, there's no guarantee I can solve it with the methods I'm doing here, unless only two of the roots are either non-real, two of the roots are irrational. If all the rest of the roots are rational, then these methods will work. So let's look at an example. Here we have p of x is 6x cubed plus 23x squared minus 6x minus 8. So I'm going to just type this in the calculator and graph it. I started just by doing zoom standard. Not the best window, but we can see actually it crosses the axis 3 times. So we're going to see the x-axis, that is. So that will be our 3 real roots. So we definitely know for sure it has 3 real roots. Okay, 3 different roots. So looking at the table, we can also see some things here. Notice that we just kind of stumbled across one. Negative 4, 0, that's one of the roots. In the 0, negative 8 is a y-intercept. Negative 4, 0 is an x-intercept. Then we also see a sign change here. Look at the y's. Positive y here, 15. Another positive y of 15. A negative y of negative 8 in between. So that says between, so we see a positive at 15 and a negative at negative 8. That means in between those x values, between negative 1 and 1, there's a root. There's also one between 0 and 1, because we have a y value of negative and a y value of positive. So the intermediate value theorem says if you have a continuous function and it has two y values, negative 8 and negative 15, then in between it's got to take on every possible y value, including 0 in that interval. So somewhere between there it must have some root. So we might look at this a little bit closer up. Well, actually further out for the y's and closer up for the x's. Maybe a little higher up would have been better on the y's to see the maximum that we're missing right here. But we're mainly interested in the roots, so this gives us a pretty good view of the roots. This one happens to be exactly at negative 4. We'll double check that in a minute, but it looked like the table told us that was exactly negative 4. And these are between 0 and negative 1, and between 0 and 1, these two other roots. So since negative 4 appears to be a root, okay, here I did change the window a little bit here so I get a pretty good view of it. So this is a nice view of this particular one, because you can kind of see the end behavior. You know a cubic, it's going to go down on one end and up on the other. Positive leading coefficient, so we see up on the right. you could possibly have a max or min, which this one does. You could have up to 3 roots, which this one does. One inflection point in here somewhere. So now we can use that. Whoops, let's go back. Where are we? Come on. Okay, there we are. So let's go through here. And we can actually use the calculator to approximate the roots. It looks like we could find them exactly here. So we did a calc 0 here, and it turns out to be negative 0.5. That's a negative 1/2. And we also calculated the other one. It turns out to be 2/3. So it comes out to be 0.6666. Looks like 6 repeating. Quit and tap X, and then change it to a fraction as 2/3. So actually we know all the roots are negative 4, negative 1/2, and 2/3, and we factor it as 6 times x plus 4 times x plus 1/2 times x minus 2/3. We can double check that this is right by putting both versions of these formulas in. One is y1 and one is y2, and then check it here, and we'll see that. Of course, if we were put in x's of negative 4, negative 1/2, and positive 2/3, we would get y's of 0. And of course, if we put in x as 0, we get y as 8. So those are both our x and y intercepts there. Alright, let's try another one. So again, we've got a cubic here, 4x cubed minus 3x squared minus 40x plus 30. A little trial and error, maybe looking at the table, maybe looking at the graph. A little trial and error, I typed this in and I came up with this window. I think this is supposed to say negative 5 to 5 for x and negative 50 to 80 for y. And we got a nice looking graph. That looks like the interesting part of a cubic. And it looks like we can see the x-intercepts there. 3 distinct roots. So we're going to have 3 distinct factors. So we're going to have 4 times x minus root 1 times x minus root 2 times x minus root 3. We just got to find root 1, 2, and 3. And so I do a calc 0 over here, try to change to a fraction, and it doesn't do it. So there's a good chance that that one might be an irrational number. The change to fraction command is not perfect on the calculator, so if the fraction in reduced form does not have a denominator that's 3 digits or less, it's going to not work right in terms of changing it to a fraction. So we really don't know what that one is exactly, but we do know it's about negative 3.16. We'll come back to that one. Let's try these others. Well, trying this one here, we get 0.75. That's 3/4, so we know that one for sure. And then this one, hey, look at that. It's the opposite sign of that one we came up with earlier. But we do know that 3/4 appears to be exactly one of the roots. So now we can do synthetic division and get the depressed polynomial here. Okay. And so we do it this way. We pull out the put the coefficients down, 4, negative 3, negative 40, 30 right here. Put the root in 3/4. So the factor is x minus 3/4. So bring this down, 4. 4 times 3/4 is 3. Negative 3 plus 3 is 0. 0 times 3/4 is 0. Plus negative 40 is negative 40. 3/4 of negative 40 is negative 30. Plus 30 is 0. We knew it was going to be 0 because of our graphing calculator. So that tells us that x minus 3/4 is actually a factor, and more than that, it tells us that the other factor is negative 40 plus 0x plus 4x squared. In other words, 4x squared minus 40. Now I can easily factor the 4 out of that, which we knew was going to be our initial term, and that gives us x squared minus 10. You can factor that with the difference of squares pattern, as long as you put that as the square root of 10 as the square root. So it's x squared minus the square root of 10 squared, so that factors as x plus the square root of 10, x minus the square root of 10. And now check the square root of 10, and we should get 3.1622777. Double check this to make sure it's right. Put it in here. That should say that's a 4 under the black box there. 4x cubed and so forth. The original, put in the factored version here. Check the tables. They match up. So it does check. Alright, here's a little bit harder one here. A 6th power. 12x to the 6th minus 1164x to the 5th, and so forth. Okay, So we're going to graph this. Takes a little while to experiment to get a good window. Here's a Graphmatica graph of it, and here's a graph. It shows pretty much all the interesting things. How do we know this is all the interesting stuff? Well, let's see. It looks like we have a multiplicity 3 root here, a 2 root there, and a 1 root there, so that totals up to 6. It is degree 6, I believe. Yes, it is. So that's all the roots. Okay. We do know that on the ends it should be pointing up. Leading coefficient is positive, so there on the right's pointing up, even, so the other degree, so the other one's pointing up as well. So notice we have a global minimum here, local maximum here, local minimum here. Inflection point right here at this root. There's another one in here, another inflection point in here, and one in here. Okay, so it looks like 3 is going to be one there. It looks like a half there, and then unknown over here. Let's check that out. Actually, a third, negative 1/3. It looks like. Could we be sure those are the right ones? Well, we could check them by plugging it in the calculator and making sure those are zeros. We could actually do a calc 0, particularly for this one over here. Change to fraction. See, it's negative 1/3. Now, because of the shape of the graph, you know this one's multiplicity 1. It goes straight through. This one touches and turns around. That's multiplicity 2. This one's multiplicity 3. That totals up to 6. So that means we know what the factored version is. Still the same leading coefficient of 12. We get x plus 1/3, x minus 1/2, and x minus 3. And the powers of the multiplicities here, 1, 2, and 3. Again, what do? Let this one be a y1, the original, let y2 be the new one, and check your table to make sure there's no mistakes there. Alright, let's do the next one. This is a 10th degree polynomial, so we're looking for 10 roots altogether. Now, some of them may be the same roots over and over again with higher multiplicities, but we should find 10 things altogether. Well, first of all, notice that that everything's got an x cubed, in fact a 4 as well, so I can go ahead and factor out a 4x cubed, leaving this 7th degree polynomial. Well, x cubed is x minus 0 cubed, so that tells you that 0 you can plug in here, of course, and you'll get 0 for y. So 0 is a root, and it's a root of multiplicity 3. Okay, so we need that there's 7, so we know that, well, we've already got that factored out. So then we can look at what's left there, the 7th degree polynomial, and the other roots are inside of there. So, well, a little trial and error. We get this graph right here. There's your multiplicity 3 root at 0, looks like we expect. And looks like here between 1.5 and 2 we got a simple root, multiplicity 1 root. Another multiplicity root between negative 1/2 and 2, negative 2. Negative 2 looks like a multiplicity 2 root, and 3 looks like a multiplicity 3 root. Let's count those up. 3, 4, 5, 6, 7, 8, 9, 10. That's all 10. So that looks like what we have. You could double check that 3 and negative 2, of course we know 0 is going to work, but you could check your table and see that 3 and negative 2 are going to work. And we got these other two to kind of figure out what they would be. So now let's do our synthetic division. Notice our original here is 1, negative 5, negative. We don't do it with the ones up here. We do it with this depressed polynomial. 1, negative 5, negative 8, 60, 15, 243, 0, and 324. I believe that's the numbers I have right here. So I'm going to kind of leave out. So when I did synthetic division up here, let's see. Here's an example. These middle row, I'm going to do that in my head and only write down the bottom row here. So here we go. We bring the 1 down. 1 times 3 is 3. Plus a negative 5 is negative 2. 3 times negative 2 is negative 6. Plus negative 8 is negative 14. 3 times negative 14 is negative 42. Plus 60 is 18. 3 times 18 is 54. Plus 15 is 69. 3 times 69 plus negative 243 is negative 36. Negative 36 times 3 plus 0 is negative 108. Negative 108 times 3 plus 324 is 0. So now your depressed polynomial is this right here. We should be able to get this. It looks like it's multiplicity 3 from the graph. So let's check that. We should be able to divide it out 3 times, but not 4. So let's divide out a second time. Bring down use the depressed polynomial here and do the division. Bring down the 1. 3 times 1 is 3 plus negative 2 is 1. 3 times 1 is 3 plus negative 14 is negative 11. 3 times negative 11 is negative 33 plus 18 is negative 15, and so forth, and we see that we get a zero remainder. Do it another time. It should work again. Use this depressed polynomial, divide it out, and we get this polynomial. We do get a zero remainder. If we try it again, just looking at it, it could be maybe a fifth multiplicity root. Well, it's not. We don't get a zero remainder. So this part here just doesn't count. So here's our depressed polynomial here. Negative 12 minus 12x plus x squared plus 4x cubed plus x to the fifth. And so, x to the fourth. Powers are 0, 1, 2, 3, 4. And so there's our depressed polynomial there, where when we factored out the x minus 3 cubed, don't forget our 4x cubed we already had factored out. So now we're down, now we've accounted for 6 of the roots, 6 of the 10 roots. 0 3 times and 3 3 times. So now the other roots are inside of here, and based on our picture here, and maybe a calc intersect on our calculator, we should think that, or not a calc intersect, but calc 0, we think that negative 2 is a root as well, twice. So check out with the long division. Here's our depressed polynomial. That's this, what's in this parentheses here, 1, 4, 1, negative 12, negative 12. Try negative 2. 1, bring down the 1. Negative 2 times 1 is negative 2 plus 4 is 2. Negative 4 plus 1 is negative 3. And so forth. We get a zero remainder. Then do it again, another zero remainder. And now this is our final depressed polynomial, x squared minus 3, which we can easily factor out as x plus the square root of 3 and x minus the square root of 3. So these two, this one right here is square root of 3, and this one over here is minus square root of 3. And they're simple roots, multiplicity 1 roots. And so we have it factored. Okay, and so we can check that out. So the factoring corresponds to the roots in multiplicities. 0 is a root of multiplicity 3, 3 is a root of multiplicity 3, negative 2 is a root of multiplicity 2, and square root of 3 and negative square root of 3 are both roots of multiplicity 1. Even if the last two are not real, we can, once we get it down to a quadratic here, we can use the quadratic formula to find those last two roots. Okay, here's some examples for you to try, and some more examples down here to try to also work with and describe what you see. Then there's a series of practice problems here for you to work on, and after you finish those practice problems are solved with this set of solutions here, and so you can go through those notes and check that yourself. So I'm going to leave that as a homework problem.